Okay, so let's talk about precision and accuracy. Now, again, this is one of those situations where in everyday language we tend to use these two terms as if they mean the same thing. But in the sciences, of course, there's a difference. Now, precision refers to how closely repeated measurements approach one another. So if you're given a task of repeatedly measuring an object, or measuring some quantity, then how close these repeated measured values are to each other, that is what we mean by precision. Now, accuracy refers to how close measured values are to a quote-unquote true accepted value. Now, to illustrate the difference between these two, let's say you're using a dartboard, you're throwing darts on a dartboard. Now, the middle of the dartboard represents the true value, while where the dart hits the dartboard represent an attempt at measuring something. So if you look at the first dartboard here, where you have these three darts all over the place, but nowhere near the center, and they're certainly not close to each other, then this represents a situation of low accuracy and low precision. In the case of this dartboard, where the three darts are close to each other, all right, but of course they're not near to the center, then this represents a situation of high precision, but the accuracy is low because the darts are far from the center. Now here, the darts are relatively close to the center, but they're still kind of spread out. So in terms of precision, this represents a low precision situation, but the accuracy is relatively high. And then here, which is of course, is the perfect situation where all the three darts are right at the center of the dartboard. This represents a high accuracy and high precision situation. So of course, whenever we do experiments and we take measurements, this is of course what we're aiming for, right? We're aiming for high accuracy and high precision. Now, in terms of reflecting the level of precision in a measured value, what we want to make sure is that whatever measured value that we obtain, that we're not claiming that our data is more precise than it actually is, all right? And the convention that we use to reflect the precision of our measurements is the number of what we call significant figures expressed in a measured value. So what do we mean by a significant figure? Well, to illustrate this concept, we're going to talk about what we mean by a significant figure later on. But let's say, for example, you want to measure the mileage of your motor vehicle, your car, and you fill up your gas tank. Let's say the volume of your tank is 14.1 gallons, and you were able to drive 273.0 miles on this much gas. So therefore, if you're to calculate your mileage, then you divide the 273.0 by the 14.1 gallons. If you do that on your calculator, you're going to get this. Now, of course, you would not be able to predict based on this calculated value, especially with so many decimal places reflected here. You would not be able to predict exactly how far you can go on a gallon of gas to this extent. Which means, of course, that you have to get rid of some of these digits because some of those digits are basically meaningless. So the question now becomes, which ones are the digits that you're going to get rid of? Okay, so when we talk about significant figures in a measured value, we're talking about those digits that are known plus one estimated digit, all right? So in any measured value, and what you have to keep in mind, measurements are basically at best estimates. Now, there are some digits that you will be certain of, but there's one digit that you have to estimate. And collectively, that one digit that you estimate, along with those digits that you're certain of, those are known as significant digits. So, for example, let's say you're given this as a measured value, represents some measured quantity, mass, length, whatever, right? Then these first 5 digits are known based on whatever instrument that was used to obtain that measurement. But the last digit would of necessity be an estimated digit. All right? Okay, so just to illustrate how we obtain those digits that we're certain about and, of course, the estimated digit, we're going to use the example of reading a thermometer. So you'll notice on the screen, we have 3 thermometers here. All right? Now, let's start off by looking at this thermometer here. Now, you'll notice that the mercury level here is just above this mark here. Now, let me just say this. The first thing you should recognize is what each division represents. So we have 20 here, we have 30 at the top here, and we have 10 equal divisions. So obviously that means that this line represents 21 degrees, this line represents 22 degrees, this represents 23, 24, 25, and so on, all right? So you'll notice that the mercury here is just above the 21 degree mark. So we are certain that this is 21 point something, right? What we are not certain about is the digit that comes immediately after the decimal point. So we know it's 21 point something. We're certain about the 2 and the 1, which makes up the 21, but we are not certain about the digit that comes immediately after the decimal point, which follows the 1. So in this case, it turns out that the actual answer is 21.2, right? But, you know, another person could look at this and say, well, this could be 21.3, right? That is just as reasonable a conclusion that somebody could draw. So, you know, if I were to give credit to a student who was asked to read the temperature here, if that student said 21.3, I would give that student full credit because we're not certain about, as I said before, the digit that follows the decimal point. So therefore, in this particular example, there are 3 significant digits being represented here. The 2 and the 1 that we're certain about, but this 2 after the decimal point, or 3, or whatever the digit is, that comes after the decimal point, that we're not certain about. That's an estimated digit. So collectively, we have 3 significant digits represented here. Now, in the case of the second thermometer, you'll notice that the mercury level is at the 22 mark here. In fact, one might be tempted to say, well, it's exactly at the 22 mark. Now, because this scale is the same as this scale, we have to show the same level of precision as we did in the previous example. So even though you might be tempted to say that the temperature here represented is 22, you actually have to put a digit after the decimal point. And by the look of things, it's on the 22 mark, so therefore the temperature being represented here would be 22.0, all right? And again, it's expressed to 3 significant figures. Now, in the case of the third thermometer, you'll notice that in addition to the divisions that we saw over here in the previous 2 examples, you have some smaller divisions between the unit values. So, for example, you have this represents 21, this represents 22, and so on, but you have some smaller divisions here, right? So that makes for a better measuring in terms of increased precision. Now, let's see if we can determine what temperature is being represented here. Now, you'll notice that the mercury level here is above the 22 mark, right? So the question now becomes, what digit comes after the decimal point? Now, each of the smaller divisions would represent 0.1. Now, from the look of things, this mercury level is just above the 0.1 mark, right? So therefore, we are certain that this is 22.1. What we're not certain about is the digit that comes after the 1. So, you know, one could make an estimation and say, well, the temperature being represented here would be 22.11 degrees Celsius, which it actually is, and therefore the number of significant figures represented here would be 4 significant figures, because you have this 2 that you're certain of, this 2 you're certain of, this 1 you're certain of, but what you're not certain about is this 1 here occupying the 100th place because it's an estimated digit. So therefore we have 4 significant figures, and therefore what this shows you is that the scale represented by this thermometer here will give you a greater precision, a greater level of precision in terms of recording the temperature compared to the other 2s, because of the smaller divisions that exist between the unit degree divisions. Okay, so I hope that this explains how we obtain the correct number of significant figures coming directly from measuring based on a scale that is provided. In this case, the scale is provided from the thermometer. Okay, so let's talk about how do we determine the number of significant figures if you're given a question where you're given a measured value, right? And you're asked to determine the number of significant figures. which will become important later on when it comes to calculations, right? So what you see here on the screen is a list of the rules. First rule says that all non-zero numbers or digits are significant. So all digits from 1 through 9, whenever they appear in any measured value, those digits are significant. The second rule says a zero is significant when it is sandwiched between non-zero digits, right? So if you have any zeros that appears between non-zero digits, then those zeros would be significant. So for example, 401, the zero here between the 4 and the 1 would be significant. So therefore this has 3 significant figures. And then in this case, even though you have a decimal point here, the fact that you have 2 zeros here sandwiched between the 3 and the 6 makes those zeros significant. So therefore the total number of significant figures here would be 5. All right? The second rule has to do with situations where you have zeros at the end of a number and there's a decimal point. And according to this rule, those zeros are significant. If you have zeros at the end of a number and there's a decimal point anywhere in that number, then those zeros are significant. So for example, in this case here, 55.000, all these zeros are significant because of the presence of the decimal point. And therefore, the total number of significant figures expressed here would be 5. Now, number 4 deals with a situation where a zero is not significant. It says here a zero is not significant when it is appearing before the first non-zero digit. So in this example, there's only one significant figure here because we have 3 zeros here that appears before the first non-zero digit. And then another situation where a zero is not significant is if you have zeros at the end of a number and there's no decimal point present. Such as in this example here, as you can see, there's no decimal point indicated. So therefore, all these zeros here are not significant. So therefore, there's only one significant figure represented in this number. Okay, so these are some rules that you simply need to know. As you're going to see later on, when it comes to calculations and rounding off, you need to know the number of significant figures that you're working with in your calculations. So you need to know these rules. Okay, now what you'll find is that in any calculation, any scientific calculation that you will engage in, you need to recognize that there are 2 types of numbers that you will be using. The first type of number is what we were discussing earlier. These are known as measured values, all right? Basically, as it suggests, these are numbers or data that is obtained from some measurement, all right? And the thing about these measured values is that they have a finite number of significant digits. The other category of numbers are known as defined numbers, right? And defined numbers can fall into one of 2 categories. Let me rephrase that. The other category of numbers is exact numbers. And there are 2 categories of exact numbers. You have defined numbers and you have counting numbers. And what they have in common is that they both have an infinite number of significant figures. Now, counting numbers, let me deal with that firstly, because that is easiest to define. As the name suggests, these are numbers that are obtained by counting. So if you have the number of students in a classroom or the number of cars on a particular road, those are examples of counting numbers. Of course, those are not measured numbers because in obtaining those numbers, you did not use an instrument to determine those numbers. Now, as far as defined numbers, as the term suggests, these are numbers that are obtained by definition. So for example, the relationship between the meter unit and the kilometer unit, those numbers indicated in this relationship are defined numbers. 1,000 and 1 in this relationship are defined numbers because, of course, those numbers are obtained as a result of the definition of the kilo prefix. Kilo means 1,000, so therefore 1 kilometer is equal to 1,000 meters, all right? As I said before, counting numbers such as the number of people or a number of beakers, as you can see, those are also other examples of exact numbers, right? So just to recap, 2 types of exact numbers. You have defined numbers and you have counting numbers. Counting numbers are obtained as a result of counting a number of items. Defined numbers are, of course, numbers that are obtained as a result of a defined relationship between different quantities. Okay, and also let me just say, again, just to recap, what they have in common is that they have an infinite number of significant figures. Okay, we're going to stop here, and then the next video will deal with how to deal with significant figures when it comes to certain mathematical operations. Okay, until next time.